So what are some of the items that are matter? So we have solid, liquids, and gases inside the classroom. What are some examples of solid, liquids, and gases inside the classroom? Brecken, what's one of them?
The jacket.
The jacket. Okay, solid, liquid, or gas?
Solid.
Solid. Okay, Wesley.
The chair.
Chair, solid, liquid, or gas?
Solid.
Solid. Micah.
An ice cube.
Ice cube, solid, liquid, or gas?
Solid and a little bit of liquid.
Solid and a little bit of liquid. Yeah, it's going to change, right? It's a solid in that form for sure. Okay, Amelia.
A book.
What about it?
Solid.
It's a solid. Okay. Anybody got anything else? Zoe.
Air.
Air. Solid, liquid, or gas?
Gas.
Gas. All right, Marcos.
Can.
Can. Oh, a can. Okay, solid, liquid, or gas?
Solid, and also technically it could have been a liquid to mold it.
Okay. All right. It could have been a liquid at one point, so it might have changed property. Yes, London.
A
Clock. Solid, liquid, or gas?
solid.
Boom. All right. One more. Wesley.
Does oxygen count as air? I said that.
Oxygen counts as air.
Oh.
So gas though, or solid or liquid? What is it?
Gas is
Is oxygen a gas, a solid, or a liquid?
it's a bit of liquid and a bit of solid. The liquid turns gas.
Okay, we got gas.
Turns into gas.
All right, here's what I need you to do. Come over to the carpet for me. Leave your journal or leave your notebooks on your table.
Michael barely has to chair. Goodbye. You're unperfect.
All right, so we're gonna lock in here. Please put your drink back on your table. Okay, so you guys gave me a short list of things that are solids, liquids, or gases. What did we have more of? Solids, liquids, or gases listed? Zoe?
Solid.
Solids. Why do you think that is? You go ahead. Keep going.
It might not be a good thing to have gases in here.
It might not be a good thing to have a bunch of different gases in here, yeah? Brecken?
Well, because say you're going to open a book, you wouldn't want it just to go right through your hand
Yeah.
to the liquid.
For sure, yeah. You can't have a liquid book necessarily. You don't want a bunch of different gases going in here because that could be dangerous, right? Flammable and all that fun stuff.
Depending on what
So it would depend on what kinds of gases. Our room is made up of primarily solids. Outside of the water and the hand sanitizer and a couple of the other beverages we have in here, coffee that I drink all the time, right? Outside of that, it's really just solids, liquids, and then you have your gas, your singular gas kind of going through here. Until we get later on into science and we start making some different types of weird forms of things, and we'll figure that out when time comes on different properties of gas. But for now, I have a couple of questions we're going to move into. Do you see these jars? I have this jar. Yeah, this jar. I have this jar.
Partly air in there also.
And what's in that?
Gas.
Absolutely.
There's air in all of them.
There is air. Okay. So you guys were able to identify the properties of this. But let's think. How much space does this solid actually take up in the jar? If you could define how much space it takes up, how much space is it actually taking up? But before we say that, real quick, somebody give me the definition of matter. What is the definition of matter? Wesley?
The definition of matter is what atoms make up.
No. But atoms are part of it. London?
It's a solid liquid or gas that can come from each other.
Okay, it's a solid, liquid, and gas, and they can turn into one another. Yes, those are properties and phases of matter. What is like our overall working definition of matter, Daniel?
Anything that has mass and takes up space.
Anything that has mass and takes up space, and you did a good job of using our clue that was on the back table, or our little whiteboard. So, anything that has mass and takes up space, do these blocks take up space?
Yeah.
Yes, right? So, these blocks take up space. How much space do they take up? London, what do you think? About a quarter of the jar, I agree. About a quarter of the jar, right? Do they take the shape of the jar?
Not really.
Not really.
Kind of in a way.
The squares kind of in a way because like they're free flowing and they don't take up the whole thing. But do the squares themselves, the little cubes themselves, change shape? No. Why do you think that is? Brecken?
Because it's not liquid.
It's not liquid. Yeah, that's true. Amelia?
I think it's because the molecules are tighter packed together.
I think it might be because the molecules are tighter packed together. You're ahead of me. Because we're getting there. Good job. So yes, the molecules in solids are more tightly packed together. So our solid cubes, here's our little mini cube. I'm going to draw one of those. Those are our solids. I'm going to draw a big square here. This is like if I took a picture and then zoomed in as far as I possibly ever could zoom in on a solid, on a little solid particle. So solids, the little particles inside a solid are all super tightly packed together. And they can't move. And they're just in there. Super, super close. This is our solid. No room. They're all just wedged in there, super, super tight and squeezed in. Okay? This is a solid. This is the reason why these right here don't just take the shape of the container. Right? They're still cubes. So I'm just going to take this little, I don't even know what shape that would be, but here, I'll take this one.
Like a car.
Here, cube.
It's a bus.
And I have a graduated cylinder here. We're going to use these tomorrow. But,
Ready to graduate?
so I have this little square. You see this? Yeah?
Uh-huh.
Got that? Okay? When I drop this in here, it stays its same shape, right?
Amazing.
The fake wow factor of it. Right? Yeah. Round of applause. So it's the same, right? And as Amelia said, the reason for that is because our particles inside these little cubes are so tightly packed together that they hold their shape. So a solid, is matter that takes up space, has mass, and it holds its shape. Right? It has a definite shape. It doesn't change. You notice when you like have to break a rock or something like that, the chunks fly off? That's because those are still trying to fight and holding their shape. So if I take one of these off, right, the whole thing doesn't just melt in my hand. But the square, this little cube, is still going to change its shape. I can drop it, still a little cube, right? I can chuck it across the room, it's still a little cube.
Look, you can
Right?
put it together.
Like that,
They have it.
Gentlemen. So, that brings us to water. If solids have definite shape, they have mass, and they don't change to their container, what do we think about liquids? Think about these liquids. Micah?
They're tasty.
Liquids are tasty. What do you think about the actual scientific properties of liquids? Because not all liquids are tasty. Brecken?
The molecules aren't really tight back together. They're they can move a lot.
Okay, so maybe the molecules, the little particles can move a little bit more. What would that explain? If they could move a little bit more, what would that explain? Why would that be a beneficial thing for them, Daniel?
It's able to make it so that they move so the molecules move so fast that it changes shape.
Okay, so you think the molecules just being able to move like that allow it to change shape? Sure. All right, so how much of the container is our water taking up right now? About how much? Just take a good guess. Marcos?
From what it looks like, it's taking up like half a quarter of
So
it.
not even a quarter?
1/10.
Okay, so we have about a tenth of the jar, maybe. Okay, so but it is taking up space in here. You can see it, right? You can see that it's taking up space. Is it still taking up space?
Yeah.
Is it taking up any less space in the container?
No.
How about now? Is it taking up any less space?
No.
But you can't see it.
Doesn't matter.
Doesn't matter?
It's still taking
Right?
up space. We can't
Right.
see the air in there, but it's still.
So there's still stuff taking up space, right? So this is still taking up space. It does not have a definite shape though, so it's not a solid. And what we have, spilled a little bit. It is changing shape on me. But you guys know when I pour this in here, it's gonna do what? It's gonna do what, Amelia?
It's gonna take the shape of the graduated.
It's going to take the shape of the graduated cylinder, right? It changed shape. Does it take up any more space in the graduated cylinder than it did right here?
No.
Does it take up any less space?
No.
Now-
Because the drops in there.
Oh, the little droplets, right? Outside of the little droplets that I have on my leg and the little droplets in here, it does take up a little bit less space. Right? But for the most part, in general, it's the same. Just assuming that all the droplets got in there. Okay. So that's our water. So that's what we know about water. It does take up space still, but it does not have a definite shape. So, what do the particles look like?
They're very small.
What do the particles look like, London? They look like they're in quarantine because they might be all spread out. All right. Amelia?
I think that they might be a little bit less packed together than the solid because it can move around.
Okay, a little bit less packed together than the salad because it can move around a little bit. Here's what I want you to do. I want you to go back to your notebook here in a second. Hold on. On a blank space. So on like whatever free space you have in your notebook, you're going to make a square just like I did. You're going to draw the solid particles. Then you're going to write liquid. You're going to make a big square. And you're going to wait right there. And we're going to draw, we're going to draw liquid particles together. And we're going to show you what it looks like. Then after that, we're going to meet back at the carpet and start up with gas particles. Okay? So go ahead, do that really quickly. You have about 2 minutes to get that done. If you finish early, just come back to the carpet for me, and we will move on.